In this unit, we'll be taking a look at our final type of isomerism. This will also be our final type of naming convention, conveniently. In order to understand the enantiomer, we need to understand a concept called chirality. Chirality has to do with a non-superimposable mirror image. What does that mean? Let's take a look. Here I've got just a plain dotted line. We're going to pretend that this is a mirror and that objects on this side will get reflected over to this side. So let's take a look at what this looks like. If I've got just my water bottle here, I could draw it out. Shouldn't take too much. I'm sure I'm a good enough artist to do that. Something like that. It's got that space in the middle. Great. If I take the mirror image of that water bottle and put it on the other side here, it's more like a alien. Whatever. So they're not exactly the same due to my drawing skills, but either side of this mirror, it's really the same image. I could pull this one out, bring it over, place it on top, and it's the same image. They are superimposable. I can put this one over the top of it. That's what superimposable means. It doesn't matter that they are a mirror image, they're still the same. But what if I were to take the mirror image of my coffee cup? If I draw my coffee cup up here, my coffee cup says, "My favorite people call me Nana." So I write Nana on here. And then I take the mirror image of that. Notice, my ends are backwards. My handle is on the wrong side. This is not superimposable. I can't just pull it out and place it over. A really convenient example for this is your hands. Your hands are mirror images of each other, but they're not superimposable. You can't just put one over the other, right? They aren't exactly the same. This is called chirality. It has a mirror image that is not superimposable. What would that look like on a molecule? I have here chloroiodomethane, CH2ICl, okay? Let's take the mirror image of that. Let's see if it is chiral or not. All right, I've got this drawn out, and if I pull this out and put it over this one, it doesn't match, but this is a molecule in 3 dimensions. I could just turn it, couldn't I? I mean, I should be able to just turn this around. If I pull it out and turn it around, wouldn't it fit over the top of that? Well, let's find out. If I make a little model of these, I've got, this one is, yep, we'll say the orange is iodine, the green is chlorine, and over here, got the same thing. So I've got these 2 molecules, and if I just pull this one out and turn it, oh, put that one on top. There we go. I just have to turn it a little bit, and it matches up. And then my orange is on the bottom, my green is on the right side, and I've got hydrogens on top. So that would not be chiral. That would have a mirror image that it can superimpose. However, if I make one change to this, one change, and you can see this, if you put together your own ball and stick model, this becomes very apparent. Let's just turn that into a hydroxide group, which I'll represent with red, these little red balls. So I switch out one of my hydrogens for a red, and now I have a chloroiodo methanol. There we go. Good job. So let's see. Let's make sure. Yep, that one's all set. So there's my iodine. There's my hydroxide, there's my chloro, there is my hydrogen. And this one, here's my hydroxide, hydrogen, chloro, iodine. Now I've got these two molecules. Can I superimpose these? Well, if I bring this over, I can see that my chlorine and my hydroxide are in the wrong spots. So if I try to turn it to get my hydroxide in the right spot, well, now my chlorine and my iodine are in the wrong spots. In fact, no matter which way I turn this, there's no way for these to superimpose. There's no way for these to be able to overlap and be the same molecule. These are different from each other. Now that seems pretty arbitrary. Why would that matter? Well, especially in biochemistry, there are reactive sites on cells, on proteins that will only react when the exact right combination of molecules attaches to it. So if I've got these three in that order, and they attach to an enzyme which activates that enzyme, trying to put these three on will not activate that enzyme. Or it might activate a totally different enzyme that has very different consequences. This happens a lot in drugs, in biochemistry, because pharmaceuticals require a very exact reactive site. And just a little bit different, just a small difference, can cause pretty catastrophic reactions. Anything from a morning sickness pill causing birth defects to, well, that's the extreme example. But even small things like scents, like the scent of a lemon and an orange, is due to just one point on a molecule being switched around. That's it. Everything is the same except for one single chiral center, and it results in a completely different scent. So we need to be able to figure out if a molecule has this chirality or not. Thankfully, we can kind of see right off the bat that it didn't work when I had a carbon attached to two things that were the same. This is going to be true in all fronts. I'm going to need to look at carbon atoms, and they're going to need to be attached to four distinct things, okay? Four distinct molecules. If I have carbons in a carbon chain, it has to be attached to four distinct molecules, okay? So let's look at some examples. Our first example here is just an alcohol on a pentane chain. The first one right here, I've got the OH group tilted back, which means that I have a hidden hydrogen here, which is going to be on a wedge. It's right there. So this carbon right here is attached, I can see it this way, to a CH3, to a 1, 2, 3, C3H, that'll be 2, 4, 6, 7. It's attached to a hydrogen, and it's attached to an OH. So those are four distinct groups, so that would be a chiral carbon. And we call this a chiral center. Now this one right here, this would be a carbon attached to the same groups on either side. However, it's attached to two hydroxide groups. Now those are going to be the same. So it doesn't matter if I flip these around, that would be the same molecule. So that is not a chiral center. So we are looking for carbons, specifically carbons, because carbons can be attached to four things, but we haven't seen anything else in organic chemistry that will attach to four distinct compounds. So it's got to be a carbon, and it's got to be attached to four different things. Now, so far this is just for carbon chains. We're going to look at rings in just a second. But it's got to be attached to four distinct molecules, okay? So that's what we're looking for in chiral centers. I want you to look at this here. Notice, I can flip this mirror image, pull this out, see that they're not superimposable, but we're going to be able to make this fit. I've got this molecule built out right here. So this green group right here, this is the chlorine. In order to see that a little better, I'm going to pull off all these yellow balls. These are all the hydrogens. They're not important right now. They're all hidden on this image, and I'm only going to leave the one that's actually attached to this chlorine, okay? So I'm only going to be leaving my dashed hydrogen. So now we can see this. We can see this cyclohexane with a green chlorine sticking up out of it, coming towards you. And if I take the mirror image of that, I have it looking like this. But notice, even though I can't just take this one out and superimpose it, I can just turn this molecule over twice, just 2 over, and now it fits over the top of it. So these are still the same. These are still the same molecule, okay? Now, what if I put another constituent on it? Let's add a methyl group. So I'm going to add a methyl group right here, also sticking out towards you. And now my mirror image over here, that methyl group would be right here. So now if we put those on our models, I've got this one right here. My methyl group is sticking out towards you. So just like that. If I put it on this one, my methyl group is on this carbon. Okay? So now, if I pull this out, let's even arrange these a little bit better. There we go. So now I've got this one and this one. If I pull these out, these are not superimposable. And now when I try to turn this, it still isn't superimposable. So these are now dissimilar. So I can see that just by having 2 groups on this, I have an enantiomer. But if I only have one unique group sticking off, it is not an enantiomer. Because this carbon, these are the same, but then this carbon, these are different because this carbon is attached to a methyl group where this one is just attached to another hydrogen. But if I got rid of this, well then this carbon and this one would be the same, this one and this one would be the same, and then they both meet at that point. So there's nothing different here. It's not actually connected to 4 distinct points. Okay? So we need to keep a close eye on that.